If you have the note guide, this is in the note guide. If you don't have the note guide, then just write this down. So the first thing we want to review is just how to calculate logarithms. Like, do we remember what a logarithm is? Okay? So some people are saying yes, and some people are saying no. Okay, so a logarithm is like a question, right? It totally relates to exponents. They give you the same information as exponents, but in exponents, you're given this and you calculate this, okay? With logs, you're given this, and the answer to the log is the exponent. So a logarithm is like a question, right? When they say log base 3 of 9, they're saying if I gave you a base of 3, what exponent would you have to put on that 3 in order to get 9? In other words, 3 to what power gives us 9? That's exactly what the log function is asking, right? And so the answer to this one is 2. 3 to the second power would give us 9, okay? So go ahead and partner up real quick and see how many of these that you think you can find the answer to, and then we'll go through and see if we actually got them right. Okay, so what did we get for the answer for part B? 5 to what power would equal 125? 3. Okay. All right, so C is a little bit trickier. 1/3 to what power would equal 27? Chloe? I can't hear Chloe. Chloe? -3. Good. So there's two ways to do this, kind of, if this is what we're thinking, 1/3 to what power equals 27. One way, as I was walking around, someone was like, when you put a negative exponent on something, it turns it into a fraction, right? Generally, if you put a negative exponent on something, we take the reciprocal of it and then raise it to that power. So the only way to get 1/3 to become 27 would be to take the 1/3 and flip it over to make it 3. So that's why there's a negative in this answer. And then 3 to what power would be 27? To the third power, like 3 times 3, right? So that's how we're getting -3. Now, the other way to do this, if that does not sit well with you, like I'm just supposed to automatically know because they could get a lot more complicated, is when you write this out to try and rewrite both sides of this with the same base. So like knowing that 1/3 is 3 to the -1 power, and 27 is 3 to the third power. Once these are the same, their exponents have to be equal to each other. Because if 3 to some power equals 3 to some power, the only way that happens is if the 3's were raised to the same exact power. So the power over here must equal the power over here. And so we would get that x is equal to -3. Okay? So you either remember what different exponents do, like this must be a negative to flip this over, and then I know 3 to the third is 27. Or you write it out like this and try to rewrite them with the same number as the base so you can set the exponents equal to each other. Okay? All right, what about part D? Log base 5 of 1. Who figured this out? Alyssa? 0. Good. Okay? So powers are a whole different universe, right? It's actually super interesting. We really learn them when we're little. Like when someone says 2 to the first power, we know that means to use 2 one time in multiplication, and that's how we get 2. And 2 to the second power is 2 times 2, so 4. And 2 to the third power is 2 times 2 times 2, so 8. Okay? And this keeps going. But the negative exponents and the 0 exponent don't really make sense with that, right? But there's a really cool pattern that happens in math. If you look at this and you work backwards, notice that each of these answers, as you go down a power, you divide by 2, right? So if you wanted to go down a power below this, and you were to divide by 2, 2 divided by 2 would equal 1. That's why 2 to the 0 equals 1, all because of the pattern that's built, not because of anything else in particular. And that's why anything to the 0 power equals 1, because if you did this with 3's, these would all be factors of 3's, and as you went backwards, you would divide by 3. 3 to the first power would be 3, and when you divide that by 3, you would get 1. So 3 to the 0 power would also be 1, and so would 5 to the 0 or anything else to the 0. And this is the same reason your negative exponents make it a fraction, because if you went backwards one more time, 1 divided by 2 would be what? 0.5 or 1/2, right? That's what 2 to the negative 1 power is. So I know it seems really weird the way that negative and 0 exponents work, but they work because they follow the same pattern that would be happening if you were raising them to higher powers, okay? So that's why negative ends up taking the reciprocal of it, because it's like you're dividing by 2, and anything to the 0 power ends up equaling 1. Okay? What about part E? Did anybody come up with a power that we could put on 2 to get negative 4? So 2 to what power equals negative 4? Would a negative exponent turn the base negative? No, because a negative exponent just turns it into fraction. Say it again. Okay, it's not 1/2, but that brings up a good point. What about when you use fractions as exponents? What do those represent? Like, what is 2 to the 1/2 power? Do you guys remember what that is from Algebra 2? Serena? Yeah, that's really a square root of 2. And 2 to the 1/3 power would be a cube root of 2. So fraction exponents just mean your number's inside of a radical. Negative exponents mean your number gets reciprocaled or turned into a fraction, as you guys said. 0 exponents turn it into 1. Is there any exponent that has a power to take a positive number and then all of a sudden make it turn negative? No. Okay? It doesn't exist. There is no answer to this. Why this is super important is this means that any time during a solving or a calculating problem, you're trying to calculate the logarithm of a negative, you can stop because that's not a possible calculation, because we always use positive bases. That's just the way logarithms are used. We don't use them with any other base. So there's no way we can ever achieve a logarithm of a negative because we can't put an exponent on a positive number that makes a negative. Okay? What about part F? 3 to what power equals 0? Good. Okay, again, no solution, because what does a 0 power do? 3 to the 0 power would become 1. Negatives turn it into reciprocals or fractions of what we were using. Okay? Fraction exponents make a radical. Mm-hmm. Right. But when you, not by negative 2, because whenever you divide, you'll never get 0, right? Because if you keep dividing by a number, unless you divide by 0, which is actually not possible, we can't get 0. So that's exactly why that's not going to work, is because we can keep dividing by 2s, and we can get smaller and smaller fractions, and they'll get really close to being 0, like 1 over 512, but none of them will actually ever equal 0. So this also has no solution. And again, why is this important? Because as we're dealing with log functions, there will be asymptotes, boundaries that say, oh, past this point you can't plug in anything, because there are certain things you can't plug in and calculate, kind of like a square root. Okay? The other reason it's important is because when we're doing calculations or solvings, anytime we come across a log of a negative or a log of 0, we can stop and say there's no solution or that's not calculatable, because those aren't things that can be calculated in the world of logarithms. Okay? Is this okay with review of how to calculate logarithms, what's allowed, what's not allowed, and kind of why that works, so it's okay in your head? All right, so we're going to go through solving some problems like this. So what kind of problems are these? Are these exponential or logarithmic problems? Exponential. They're exponential because the x is in the exponent, okay? So there's kind of two different ways that we can solve these, and it totally depends on if the numbers work really well together or not. So, for example, in A, if we were going to solve that, the first thing we want to do is we want to get the 3 with the power on it alone. We want to isolate it. So we would add 5 to both sides, okay? So when you add 5 to both sides of the equation, we would get 3 to this power equals 27. And what we do next depends on if we feel like 3 and 27 are numbers that are related to each other. Can they be written as powers of the same base? Okay? So 3 is only a power of 3, right? Unless you want to get fancy and do like 1/3 and crazy things like that that are more difficult, okay? But if you want to just stick with basic numbers, 3 is just 3 to the first power. There's nothing else that we can use. 27 could be written as 27 to the first power, like it is right here. Or it can be written as 3 to the third power. Notice that we said 3 in the base again. So if we can get the bases to match, that's one way that we can solve these fairly quickly. So that Just like we were talking about when we were trying to figure out the logs, if we can write them like this, the power in that is that knowing that these two things are equal and they both have a 3 here, means that this part of them must be equal, and you can kind of just ditch the 3s. We're not canceling them out. We're just using common sense. And so we know that this part must equal the exponent on the other part, and so x is equal to 5. Okay. However, it's not always that easy, right? Because look at part B. Can you write 4 and 5? So 4 is already alone on one side. It's all set up and ready to be solved. But can you write 4 and 5 as the same power, like the same base? So 5 can only be written as 5 to the first power without getting into fractions or decimals or something. 4 can be written as 4 to the first power or 2 to the second power, but none of those correspond with the 5. Okay? So there is still a solution. It's just maybe harder to find depending on what you like best. If you really like logs, maybe not. So this is where we use logarithms because logs and exponents are related. So in the world of exponents, we say 2 to the third equals 8. In the world of logarithms, the way to say that is log base 2 of 8 ends up equaling 3. That means anything that's written in an exponent form where you have the base, the exponent, and the value of the power on the other side can also be written in log form where you have the base, the value of the power, and then the exponent is what it equals on the other side. So when you have something like this that you cannot write both sides with the same power, this is where you guys use logarithms to help you solve. So one way to solve this, and we'll talk about both because you might have done either in your Algebra 2 class, one way is to rewrite this with logarithms. So I would write log. What's the base from that equation? 4. And then remember, an answer to a logarithm is the exponent. So the exponent would go on the other side of the equation. What's the exponent? X. This is the only reason why logarithms are useful here, because x used to be in the exponent, but now it's over here, and it's solved for, and I have something on the other side that it's equal to. What number goes inside of my log base 4? 5. This is technically the answer. Okay? And we're going to do a lot of this non-calculator, so we're going to leave our answers written like this, and we have to be okay with that. Okay, how many of you guys in Algebra 2 relied on rewriting with logarithms like this? You like your log base 4. How many of you guys took the log of both sides? Okay, so we can do that as well. So you can take the log of both sides. That would look like this. The log of this side and the log of this side. And the reason that that helps you is because there's a property in logarithms that says if you're taking the log of something that has an exponent right here, that is the same as having the exponent multiplying the logarithm without that exponent in it. Okay? So taking the log of both sides is useful because you can get x out of the exponent. So notice our whole goal is to get x out of the exponent either by rewriting or taking the log of both sides. And so then here's x. It's being multiplied by this log of 4 thing. So to get x alone, we would divide by log of 4. Now remember, when we don't write the base of a logarithm, what base does it really have? You guys remember? 10. Okay, like our number system. Okay, like how we have like tens place, hundreds place, whatever. That's why that's common. That's what it's called, the common log, or popular in our number system because we base everything on 10, so powers of 10s would be really useful. So I didn't write anything here, but it's like there's a 10 here. Because if there wasn't a base and a number, you couldn't be doing all this dividing and stuff with this. And so another way to write this answer would be like this. These are the same thing. Okay, I'm not going to go that much into it, but if you guys remember, there was a change of base formula for logarithms, and they basically said, because there's not really a button for this on your calculator with base 4, but there's a button that just says log, and that's base 10. So like if you wanted to type this in the calculator, you have to actually type it like this, log of 5, like log base 10 of this number divided by log base 10 of this number. These are the same thing. They're equivalent. Okay, it's different ways of writing them. Okay. So how many of you guys did this in Algebra 2? You took the log of both sides. You did both of them? Okay, good. So whatever you guys are comfortable with, I'll accept either answer like this. Just be comfortable with leaving it with the word log in it. Okay? You don't have to put it in your calculator. Okay? All right. Are we, because we only have a couple minutes, so are we pretty good with where we're at with, so we reviewed what logarithms are and how they're related to exponents, and we solved exponent equations either by setting the bases equal to each other, and when we couldn't get the bases equal to each other, we used logarithms, okay? So then tomorrow we're going to look at if they already have the word log in the equation, how do you solve those? And we're going to rely heavily on just changing it from like this back to that. Okay, kind of back and forth idea, and then we'll work on homework that reviews the log and the exponent stuff. Sam?